Hi there, this is Alex Busetta from Abacus team. Welcome to this video on design of experiments. And we're going to demonstrate this by using the Lean Six Sigma companion, as well as some Excel functions. First, I would like to just say a few words about the difference between a regression and design of experiments. If I look at the companion over here in the menu, so we have recognize, define, the measure phase, we have the analyze phase, and in the analyze phase we do have the scatter plot. And the scatter plot we see here, this is a fake example about alertness of employees if they go with drinking wine, eating spinach, water, etc. So a little bit of a lively example over here. So a regression, we would collect the data about what people, customers, users would do, and we would record the overall result. And here we have an index of alertness of the employee. And this index, the higher, the better. So we have quite a few rows over here, over 250 rows. And what a regression is, it means that we would run an overall function to understand what is the relationship between the y, the result, and the different x's. So in the companion, you have a few things that are already quite handy. You do have here a R-squared table that is showing here the overall correlation of the different factors with the alertness. So as you can see here, spinach has a very high overall relationship, vitamin C. And you also have the interactions. Interactions meaning, as an example here, if we drink wine and eat spinach, so wine and spinach do have an interaction on the result, or vitamin A and spinach. In the companion, you also have here some scatter plots with the overall R squares. So we can, of course, run regressions on just wine and alertness, or just spinach and alertness. But this is typically not what we want to do. We would like to find an overall regression about how everything connects to the overall result. And that's what we would be looking at next. So let's look now at performing a regression in Excel. So you need, first of all, to download for free the add-in called data analysis. And I would run it over here. There's quite a few interesting functions here, very statistical, so not as in depth as what you see in the companion in terms of all the tools. Nevertheless, if you click on regression, very interesting function here. Click on regression, and then I would select my Y, my input, my output, I should say, now result or alertness, and then we would select our overall x's, our different factors. So I will take the columns we used here, vitamin, spinach, etc. And we have everything that we need over here on top. Like the labels, I would like to have the confidence intervals. We could even select to have some residual plots. I will not do this for this demonstration, and then we would press OK. And overall here, Excel gives us an overall regression. So the first thing that we can take a look at here are the p-values, the probabilities. And we didn't add any interactions here, but we could have the interaction between wine and spinach, for example, would add a column with the multiplication, the product between wine and spinach. So overall here, I could put some conditional formatting to see which ones of those p-values are the most significant ones. And we see here, well, the intercept is just an intercept, just a constant. Wine, spinach make a big difference, as well as vitamin A. I'm looking for probability values of less than 5% or 0.05. We also have here coefficients. So we could build an equation with the coefficients. For example, my alertness equals 21 plus 1.25 times my quantity of wine plus 14 times my quantity of spinach, etc. So this is very, very useful to understand what are the significant factors. A regression is great to find relationships and to find an equation. However, it is very noisy, and there's a lot of factors that are not that significant. Nevertheless, if you look at here, the adjusted R square is 91%, which is quite good, meaning our model is quite good. Typically, we're looking for models that are higher than 64, 65%. And here we have 91%. If we want something much cleaner to be able to optimize a process or optimize a result, this is where a regression is not enough. And we will demonstrate next what is a design of experiment. So now let's look at what we call design of experiment, which gives us a much better resolution of an equation, much cleaner to be able to optimize a process. So as you've seen, the first step is to understand what are the critical factors using regression, etc. In the companion, you do have in the improve part here, the design of experiments template and guide. If we click here, you're going to see that there's a couple of things. So first of all, this video over here. You do have some templates to start from scratch, and you also have an example. We will go through the templates just first to illustrate what is available here. So I would click over here, and you do have some very detailed instructions here. First thing that I would typically do is save. Save before modifying anything. So in case I would like to delete, add, etc., I want to keep a genuine template. How this template works. On top here, you have a plan, a guide that tells you what do you want. Do we want a two-factor design of experiment? So if we identify that two factors were important, so for example, wine and spinach, I could run here my design of experiment that would be very, very crisp and clean, and -1 meaning the lowest level of wine, and 1 or +1, the highest level of wine. For example, could be no wine or 1 glass of wine. Spinach could be, for example, -1, 50 grams, and upper level 100 grams, as an example. If we want 3 factors, I would consider this equation. If we want 4 factors, we would consider all of those. So what you have in these templates is what we call full factorials, and you have up to 6 factors that you could put. So each line here is a guideline in terms of what is that experiment that would run. And on this side here, replication, it is actually my overall results. If I did this 4 times, 5 times, in this case, we ran each experiment 4 times. And what we have on the right side is the overall average and the standard deviation. In this example of alertness, we want to have the highest average, and we still want to have a small variation, a small standard deviation, so I want to have both results. What you have as well below over here is a conversion. So you see over here, for example, spinach grams, 50 grams, this is my -1, 100 grams is my +1. And so it shows what is my -1 and my +1. So this is something that you might typically use later once you have the equations and you have the design of experiment run. But I could put, for example, that I find that my optimum is 0.25 and it would give me my exact uncoded result, which would be, in this example, 81 grams of spinach. So this is the overall template. And you do have some sheets for the average and standard deviation, right? Because we want to understand how those factors affect the average and how they affect the standard deviation. So this is actually this example here, and we will walk you through a detailed example with something different than spinach and or wine, something a little bit more real. So now let's look at a full example of a design of experiment. And what we will do over here is to click on that step-by-step example here. And so it is open, and as mentioned before, it's always nice to save in another location in case we would like to modify it or do anything with it. So what we have in this particular example, we have here on top the overall experiment to be able to optimize a success rate of a chemical process. So what we have here in terms of the results, it's the percentage of success, or a yield if you prefer. 69%, 97%. And we did run over here 4 factors. So the catalyst, the agitation, the temperature, and the concentration. You can, of course, extend the columns to make things a little bit more readable as you see fit. And we did not use the other 2 columns over here. We didn't use the other rows neither. So this is what we have here is our plan of the design of experiment, and this is what we run. Once we have the results, we do have here our overall averages and overall standard deviation. So we're ready to look a little bit more in detail at the design of an experiment. We are not just going to pick the highest number here. We really want to choose the optimum, so we want to understand the model. The next step, first of all, you would see automatically these overall templates here that are populated. So the design of experiment for the average. And you have over here, you have at the bottom, first of all, some scatter plots showing you a little bit what seems to make most of a difference. And as you see, concentration seems to make a difference. Temperature, and this is actually for the average. And you also have a table here in terms of which ones of these are significant. So we see the catalyst, the temperature, concentration as well. And there seems also to have some interactions between, for example, B and D. So the catalyst and the temperature, and D and E. So so we're going to keep our D and E column here. We can suppress the other columns. We don't need them in our model. And we also need to keep B and D. So we're going to be removing here our other columns. And this is what we just need to keep. We can, of course, get rid after that of all those columns that we don't use. And now we are ready actually to run a regression. And we would do the same thing as before. We would go here to our data analysis, and we would take our regression and select here our Y which is our average, and we will select then our x's, which are all the ones that we selected here, including the interactions, because we know that the interactions make a difference. And once with this, we would go through this, then we would run our regression over here to get the full result. Before looking at the results of the regression, let's look also as what is happening in terms of our other sheet that is automatically populated, which is related to the standard deviation. So we have here our results from the standard deviation because we want to reduce variation in terms of what we want. We want a consistent success rate. So if we look at here, we see that there seems to be the B that makes a difference, C and D a little bit, so we might keep them. The other ones, we might keep them. We might keep the columns in terms of the overall results, or we could remove them. You also have here, same thing, some scatter plots showing you a little bit what seems to be the most impactful one. So here, just to try it out, we'll keep everything, all our factors, but we will remove all the interactions. They don't seem to be important. Keep in mind that if we're not sure, we could just keep them. And we would then run our regression for the standard deviation. So this is our Y, and these are our different factors. And we would run it in the same way that we have done before for the average. So we would get a regression for the average and a regression for the standard deviation. Now let's look at the results of the regression. I took the freedom to add some colors so you could see the result right away. So we would have our regression table. Our adjusted R-square is much higher, and this is typical of design of experiments because it's very clean. We just keep the factors that make a difference, so 97%. We see here that our factors that make a big difference are the catalyst in terms of the probability values, right? So less than 0.05, temperature, concentration, and then our interactions, right, that we chose, BD and DE. What we done as well, we have the coefficients here that help us build the equation. What I just did here, and this is something that is very nice with Excel, just generated here a bar graph related to these, a simple bar graph to see what seems to be the relative importance of these, and which one should we reduce, which ones should we increase. So you see here that we need to increase the catalyst. If you look at the color over here, agitation has no big effect, right? Temperature, we need to increase it as well. Concentration, we need to reduce it, etc. So we have this. What we already also done here, I just built an equation. I'll show you the equation that was built here. I built the equation based on what is on the left. So our result, our success rate is 65 plus 10.68 times the B plus 0.1 times C, etc., and including the interactions. So we could, of course, remove the factors to have even a cleaner equation here. Just for this demonstration, wanted to keep them over here. And we do have here the result, and then I can really play with the factors to see, well, if this is 1, if I put -1, if I put -0.5, and trying to find some kind of optimum in terms of what I should be getting here in terms of my overall yield to see what would be the best one overall, right? So here we could play for a while. We could also use a go to data analysis, and here you have the solver. You could also use a solver to find the better function. One thing though I would like to show you over here, let's say that this is what I would like. So these are coded, right? It goes from -1 to +1. We will be able to go back to the table that I showed you before to convert. And then I would include in that table 0.65, and the 0.65 would give me exactly what I would like to have. On the right side, we have exactly the same thing for the standard deviation. I can also play here to understand what would be my standard deviation. And I can use the solver actually to try to minimize the standard deviation and maximize my average. Right, so here I have, let's say 1.65, 1 minus 1. So I know that the yield here would be 95. Here I could type 1.65, 1, and minus 1, so the same numbers. And this tells me that I would have a predicted standard deviation of 0.86. So you could do a trial and error here, or you could use, of course, the solver. Once I have those parameters, as I mentioned, we can then convert them to what we would like to have. And we would go to that primary table to convert to say, well, 0.65 agitation, what does it mean exactly? So this was a quick overview of the design of experiment and of the steps. And I would just like to conclude and go back to our planning sheet to understand together what this is all about. So let's look at our planning sheet and what we have done as an overall recap. We ran a very clean experiment based on the factors that we knew were significant. So catalyst, agitation, temperature, concentration. We added some interactions for the average. We did not do so for the standard deviation. And we found out that some of the parameters that we wanted were, for example, 1 for the agitation, 0.65 temperature, and concentration. And we can go back to that table, and this is a table that you have here, which indicates what is the definition of 1 and -1, right? Meaning what are our uncoded data. So we see here the units, RPMs, Celsius, etc. And if we enter here 1 or 0.65, we know exactly what we need. So 20 grams per liter, 706 RPMs, temperature of 85 degrees C, and a concentration of 5. And of course, you can here still play around to understand what it means, all the different temperatures. So hopefully this is helpful as a walkthrough, and we wish that you're making your design of experiment journey very, very pleasant, insightful, and as easy as possible. Thank you very much.